All right, let's go over our discrete random variables. So here we had a situation discrete because, this was a whole number amounts of emails, 0 emails, 1 email, 2 email, and so on. And then they had different probabilities of how frequently those amounts of emails will happen. All right, now here is how many emails should the professor expect to receive each day and with what standard deviation. Okay, you cannot just put this into your calculator, which, by the way, the way you put it into your calculator was you put this information here into L1, and then you put this information here into L2, the second set of information, okay? And then you went to your calculator and you did one variable stats. So here you put in the L1, and then here you put in the L2, and then you did one variable stats of. So you did one variable statistics. And so let's not do that. One variable stats of list 1 with list 2's frequency. All right. So there is how I came up with these numbers here, 2.95 emails and 1.32 emails for the standard deviation. Okay, but if you were AP testing and this were a free response, then you would need to do something such as this and this. Okay, so let's talk about how to do that. So that is located on your formula chart. Okay, so here's the front page of your formula chart. So I'm going to zoom in. See right here, discrete random variables right there. So I'm going to zoom into that so you can see how to do that work. So see, this looks really scary, but you were summing up the number of emails times the probability of those emails. And so then you did it for every one. So therefore, see, look, I showed 0 emails and there was 0.05, and then plus dot, 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 plus the last in the sequence. This one here. So I'm always doing the first in the sequence plus dot, dot, dot to the last in the sequence because they were summing. Now let's do the standard deviation. Formula chart wise, here's how this looks. Again, scary. So we're doing the square root, and then we are summing up. So this X, that's your emails, and then minus the mean. You got this number from your result there. And then, quantity squared times the probability. So let's see how that looked here. See, this first one, 0 minus the mean, quantity squared times that probability, plus dot, 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 plus. Okay, now the last one here. 5 emails minus the mean, quantity squared times that probability. So that's the work if this were a free response problem. All right, next we are taking, now remember that you want to put the units because that's going to keep that's going to help you keep track of if you are transforming, combining, all those different kinds of things. So see here we had number of emails, but here now they want to transform from the number of emails into the minutes. So it says that it's 2 minutes on average per email. So then the average number of minutes I multiplied by 2, and I got 5.9 minutes, okay, with this standard deviation because, yes, standard deviation is affected by multiplication. All right, but suppose it takes the professor 3 minutes to boot up his computer and then 2 minutes. How does that then change the time he spends? Well, the average is affected by the plus 3. So the average got the plus 3 added to it, but not the standard deviation. The 3 plus 3 minutes did not affect the spread, shifting 3. So this was the same as part C. All right, and then our last problem here, let's see what we have. Let me pull that out there. We've got where we are then, so now that we have the mean and the standard deviation, okay, so here we have, so then now we're taking this discrete and binomial situation and turning it into the normal model. So here we go. So assuming that the distribution of times that it takes the professor to turn on the computer and answer the emails is approximately normally distributed, okay? Determine the probability that the professor would have to spend no more than 15 minutes, so that's 15 minutes or less, for the total process of turning on the computer and answering emails. So that indicated to me that I was going to be using the mean and standard deviation from D and E. So that's what I have here. And so then, so there's the mean, 8.9 with the standard deviation. So I did a z-score, 15 minus the mean over the standard deviation. And then I norm CDF'd to get this area down here. Okay, so 98.96% chance that the professor will have to spend no more than 15 minutes turning on the computer and answering the emails. All right, now we start. Okay, so now here is the second topic, combining the discrete random variables together. So here we go with that. So we had dog costs and cat costs. And so the dog costs had, both the dog and the cat had a mean and and then both of the dog and the cat's costs had a standard deviation. Let me move this down here so that we can keep track of that. Okay. So what is the expected value? Expected value is the mean for the total of one dog and one cat. So the means add together like normal. You just add them up. But remember, the standard deviations do not do normal combining, standard deviation. So combining those standard deviations, you are squaring the dog standard deviation plus squaring the cat standard deviation and then taking the square root. All right. So now once you have this distribution for one cat and one dog, you have where the center is, the mean, and then you have the standard deviation for one cat and one dog. So then we're going to find the z-score and find the probability that it takes $240 or less in annual costs. Not very likely, less than 5% chance. All right, but what is that expected difference? So this is seeing, do you know the subtraction rules? Yes, the means subtract like normal. So it is expected that the dog will cost $80 more than the cat on average in cost per year. But the standard deviation does not get smaller. It doesn't subtract. I'm not sure how much the dog standard deviation is. I'm not sure how much the cat standard deviation is. So I'm even more unsure the difference between them. Those do not subtract. It's the same standard deviation as part B. All right. So then, if the difference in cost can be described by the normal model, what's the probability that the medical expenses are higher for someone's cat than the dog? Okay, so you remember on this problem when we are comparing, so we're seeing where one's higher than the other. Okay, so we're talking about the difference between them, but in order to know where one's higher than the other, we need to know where they are the same. That's the first key criteria. Where are those costs the same? And that is a difference of 0. So that was really the key component to being able to do this problem and find that probability. So we then identified that z-score at a difference of 0 was at negative 1.74. Now, the next thing is you have to think to yourself, okay, which side is which? So if I do this, this over here on the right is the positive differences, and I did dog minus cat. So over here, the dog costs more than the cat. But over on the left, the dog costs less than the cat. So once you determine which side of that equal line is which, then what side do they want? They want it when the cost is higher for the cat than the dog. So we want it over here to the left. And so then that is how we computed that value. It was coincidence that it was the same as that problem up above. All right, moving on. But now, this is now multiple cats and multiple dogs. We had what? 3 dogs, 2 cats. Okay? So we had the 3 of the dog costs and 2 of the cat costs. So the average expected annual cost is normal there at $3,625. Okay? But here we have the next thing. What is the standard deviation? So let's talk about that. Okay, so you must combine, see each one of these dogs' standard deviations separately. So because the dog's variability was 130. I was confused. I was thinking of yesterday or the information on the previous page. So looky here, I have 3 of these dogs. So the point to this is you need to get that squared standard deviation first and then combine 3 of them. And after you do that, and then here is the cat standard deviation squared, and I have 2 of those. First, you find that out, and then you do your square rooting of it. All right. And then there is your $4,000 total, finding more than that, and you have with that mean and standard deviation. All right. So this was just an actual 2015 AP free response question, so I wanted to throw that one in there just to give you an idea of how that looked as a free response on that AP test. So here it was, at least one ATM. So that is all of these probabilities added up. And what is the expected value of the number of ATMs that are working when the mall opens? So that's expected value is the mean. So what I did was then I just found, this is list 1, this is list 2, and one variable stats of list 1 with list 2's frequency. So on average, there's going to be 1.73 of those ATMs working when the mall opens on any given day. And so then what is the probability? What's the probability that all 3 of these ATMs are working when the mall opens, given that? So it's a conditional. That's this. Do you remember this? Given that at least one of the ATMs is working. So out of the 85% of the time that at least one of them is working, what's the probability that all 3 of them are working? And there you have it, 0.2824. So this is a higher probability. So the question is, given that at least one ATM is working, would the expected value for the number of ATMs be less than, equal to, or greater than the value from part B? Is it going to be more or less? Well, it's going to naturally be more because you had that the new mean is going to be 1.73 expected, but out of 0.85. So this is the average out of the 85% of the time, again, conditional upon at least one of those working. So then that makes, on average, you're going to have 2.04 ATMs working. So you're going to have more because it's just out of 85% of the time instead of 100% of the time. All right, that was it. That took care of that was all the types of things in the discrete random variables that you need to understand and be able to compute when you're presented with those context examples. All right, so I hope that helped you there, and then we'll go on to today's notes.